Okay, so I'll send an email about where we're headed, but we don't have that much time. This is us here. Next week we'll either do geostrophic, like geophysical flows. And so we'll need a little Coriolis at the beginning. So we'll do a little bit of Coriolis for us. We'll talk about rotating reference frames. We'll see all the fun ways we can do that. Or we'll do turbulence and instability and laminar flow, kind of all jumbled together. And we'll talk about, if we want to, we can talk about like compressible flows, like shocks. Those are really cool. Aerodynamics and boundary layers, they kind of go together as well. You'll see that when we talk about boundary layers, we talk about like the pitch of an angle of a wing and how that creates lift. Right? How do a plane fly? How do a helicopter fly? Right? Now, preference for whether or not we jump right into laminar flow versus like geophysical flows. Cool. All right. I didn't think anyone would, but just thought I'd ask. Cool. Oh shit, I don't even know if I made these. I did not make the homework, but the homework will be due next Wednesday, and it will cover only these wave equations. Based on some conversations that I've been having, I think we're going to have all of our problems from now on feature 2 routes. So one is you can do like a traditional problem, and the other is you can do an example from the book, but you're going to code it. So while it's traditionally done with written words, you would then take that example that's already worked, that you see the answer to, for example, and create it in code with an analytics, with a non-analytic solution. That seem fun? Okay, and then that's a preference, right? You can do one or the other, or you can do both if you're a psychopath. Okay. Anything else? Questions, comments, concerns? Okay, what are we looking at? 1 point. Ripples, more points. What do you see about them?
It looks like it's reacting to something passing through the surface. So like something fell or is
Inference. That's not what you see.
okay.
What? Okay, there is a center. You don't know which direction they're moving.
Yeah, like changing an amplitude.
They're changing in amplitude. We're the biggest ones.
Oh, yeah.
Here?
Like towards the amplitude, probably towards the center.
Here?
Those are wave distance between us.
There's different distances between crests. There's bigger distances out here.
Yeah.
Okay. What's happening out here?
It looks kind of like. It looks kind of like.
They're plane.
Yeah, it's like they're all like horizontal.
So you don't think they're connected?
Yeah.
Interesting. So let's say I did drop a rock into water. Okay, let's say that's exactly what happened here. And it did emanate from the center. Okay. Has anyone ever done this before?
Yeah, I dropped it.
Because we have a little intuition, so we see the rings get bigger, right? Okay. And this one out here, the biggest one in wavelength, is that what we said? You ever wondered why?
Say that one more time.
Have you ever wondered why this one is the biggest?
Yeah.
Yes, you have constantly. As soon as you drop into the water, you're like, what's the dispersion relation here? Right? I know that. Like that's what Kobe told me in his off time. Okay. So we were talking about oh wait. Anyone do this again? Okay. We want to do this? We feel confident.
I feel like
We're moving on?
Yeah.
yeah.
We're ready.
Wait, bottom one. Bottom one.
The bottom one. Okay, well, let's do the second to bottom one.
Oh.
Oh.
All right, Isabel wanted to move on, so go ahead. Yeah? Yeah. Okay. Okay.
I don't know if the name.
This one? And this one? Okay, okay. So you just didn't want to do it. It's not that you felt confident in your understanding of it. Okay, so what was this one here? This is PDV work. Everyone as a group can do it like elementary school. And this one here? Pressure gradient work. Okay, so this one is I'm pushing a book, and this one is I'm changing the size of my box. So you said, okay, this is viscous stresses and this is viscous stress. Not wrong, but not informative. What does this one here do? How do I think about it? There you go, right? Hand motions. Okay, and here? God, right? All right. Now we did it. Okay, now we can put this one to sleep. We'll do it again next week. I don't go for it. All right, and this one. You talk a lot. You're good. I believe that you know it. I want someone who doesn't talk. She's out. I got her.
Okay, I know the vorticity,
Yeah, advection and diffusion. Good. There you go.
We did it. Look, record time.
Record time. Okay. So theoretically, we were talking about this undulation in the wave, right? And let me put a couple things back into our memory hole, because we're going to remember how this works at all. We have something like this. Okay, and this is Z. This is Z equals 0. And then you have some distance down here. And this is H, or I should say minus H. Right? And you have some place here that you normally would have the surface, and you have some undulation. Right? Perfect sandwich. Wow, amazing. Okay. This one. And then this one here, what did we define this as? What? Yeah, we called it like eta. That'd be the perturbation here.
Yeah.
And the whole surface is called F. So F would be defined to be Z minus eta or something like that, equals 0. And there's a relationship between the two. Okay, so we had some undulation, and we talked about, well, we think that the half line of, say, a single particle is going to do something like that. And then down here, it's going to do something like that. And I should just show you that without any motivation. Y'all believe me. Yeah. Gullible. Gullible, right? Why is that? Because I said it really like convincingly, right? Anytime a man says something convincingly, just believe him. Give me my money. Okay, there you go. I must owe him money, and then you give the money. So that's exactly not what we're gonna do. We're gonna show this for ourselves. Okay. So we have this thing. Okay. And we find these velocity fluid components. They suck. Okay, I'm gonna tell you that already. U is A omega cosh K E plus H. And if you're following along at home, that's totally okay. This would be equations 827. Cinch H plus traveling thread. Okay, I'm not going to do both of them because I don't like them. But let's think about what they really mean here. Okay. So we have a traveling wave component, and we have something with coshes and cinches. You should have no intuition for what that means. Right? Is that accurate? Yeah. Okay. So this piece here, it's really important to think about what we were saying before. So I said, you have some modulation of the wave, like this. And people were like, well, doesn't it push you? Right? You're saying like, doesn't the duck move? I'm saying both of those are correct answers. So this and this is the same answer, right? Because of the fact that omega here has a direction. As t keeps going, it moves the wave to the right. Is that clear or no? Okay. So if you are moving with the wave, it just looks like that. And if you're sitting at the bottom, it looks like the whole thing is stagnantly going over. Right? Okay. Okay. So we can do a fun thing. We want to talk about before we get to the path lines. We're gonna assume that we solved those wave equations. We got this really beautiful U. We want a relationship between omega and k. Why would we want that? What do they mean? What does k mean then? What's that? It's a not very helpful response. Does anyone have a helpful response to what k means? One over. Which?
Oh, one over, wait, what?
What
the wave number?
This was our wave number. So k was the wave number. And it was defined to be 1 over the wave number. Okay. What about omega? It looks like that, but it's not. Not in this context. We don't have enough letters, I'm sorry. Think about it just in terms of your what is it, like algebra trig? I forget when you.
Oh, it's phase speed.
It's a phase, right? So this is your phase speed. Okay. And what is this defined as 1 over?
Period?
What?
1 over the period?
Correct. Okay. So why do we want a relationship between omega and k?
You can see it.
Because then you shut up, Mateo.
You can relate how the waves are, how fast they are.
Yeah, yeah. So you have a relationship, if you think about omega and k, you're really talking about how is the wave number or the wavelength related to the period. Another way of saying that is how does speed, wavelength, and period depend on one another. For light, we see a beautiful relationship. Speed of light doesn't change. Is that normal in the world? For light it is, but for all other waves, this is strange. So we're going to talk about what we call dispersion relations. Okay, this is the best one. I'm going to keep this short one very like thicker and it doesn't snap with my manly arm. So we can simplify this dramatically. Okay, we can say something like omega is the square root of gk tanh k h. Okay. You do not need to understand how this works. How we got there, irrelevant. The important part here is omega depends on k. Omega is a function. Right? You got that. Wow. Good. So what you do is you say, you just solve for everything. What's that?
I know.
What do you say?
No, it's
Also with
he's so. Sorry.
If you want to do this, you can do it yourself. You take the stream function, which is 5, like this, and you can do this. Okay. And I think you can get that equal 0, and that will give you basically Oh, it'll give you that. It's a few steps, but the math is not what the important part is here. The important part is that omega depends on K. Okay, and then we have to do one more step. How do we relate these two to C, the speed in the fluid? Think about it in terms of like, how do we relate omega, frequency, wave number, to speed?
Thinking like the beta ratio, where it's like.
Easier.
Okay, okay.
Yeah.
Omega over beta.
Omega over. C is omega over K. Let's see if that works. K is 1 over L. So that puts the distance up here. Omega is 1 over T. So that puts the T down here. L over T is the speed. Bada bing, bada boom. Right? Okay, so then we can do this. Right? Put that in there. I think it gets rid of this step. No? What? No, this is the way.
Oh, no, is that K or? Oh, fine. Got it. Sorry, I thought it was each one. Yeah, I was like, oh, shit.
Never. This is not quantum. Keep away from me with your quantization errors. Okay. So, what does this mean? Break it down for simple math. C is proportional to what important thing here? Wavelength. Weird or no weird? Oh, weird. Let's go back 1 second here and see if it makes any sense.
Wave is one of the largest wavelength.
The fastest wave is the one with the largest wavelength. Is that true? Yeah. Oh shit. That's not a lie. Holy fuck, I can see it with my eyeballs. Right? So water waves are dispersive. What that means is I set them off in the center, just like you said. Drop a little bomb here, and then you get all of these different wavelengths. And they separate. Okay, the ones that are moving the fastest are the ones that are out here. The ones that are moving the shortest, fast. The ones that are the shortest are moving the slowest. Okay, this is called the dispersion relation. Okay, these are for surface interface waves, right? Water waves. We will get to other versions of dispersion relations, but it is an important characteristic to know if you have multiple types of waves in a packet, say right here when you started it, how do they evolve? And what it clearly shows here is that you start with, let's say you have a wave packet like this, and in it are all of these waves. Okay, and then sometime later, this wave is out here, this wave is out here, this wave is out here. And then all of it. You should see it right there. You don't believe it? That's how it works.
You need to go to a lake and show.
A what?
You need to go to a lake and show.
Yeah, you're right. Take the rest of the day off. We're going swimming, folks. Okay, so don't clap for it. Okay, so yeah. So let's work it backwards. What this is saying is that the wave speed, the speed of the wave in this formalism is proportional to the wavelength. So the initial perturbation, right? Let's say I drop a rock. It's going to create all sorts of perturbations in the fluid. The large scale perturbations, remember that waves, they're not connected to one another. So they can pass right through one another. And large waves will separate because they will start to move faster than their neighbors. Right? So in the viewpoint of the big wave here, right? If we move along with them, everyone else seems to fall behind. Or if you want to be this little one here, everyone else takes on. Yeah. Okay,
I think it was the reason why it moves faster, like, why is it faster?
just what waves do. Yeah, waves just do be like that.
Well, what makes it go faster? It's so small, why is it down here again, and then it's.
What do you mean? So remember that it's just, we just punch it once, right? So we create a series of waves all together. Then they radiate outward. Okay, the largest amplitude, or sorry, the largest wavelength waves move out faster. Right? This doesn't say anything about the amplitude. It just so happens that they're also the larger amplitude.
Also, like the initial ones that moved out farther.
They all happened at the same time.
Oh,
Right? Remember, if you drop a rock, like let's say you drop one single rock in here, this wave packet starts all together. It's a perturbation that occurs because you push the water out of the way. You create an interface wave, right? And it starts off all together and it evolves. Right? Now, the other problem is that you have viscosity in the fluid. So the viscosity in the fluid eventually makes these ones just return, right? Remember, there's a surface force issue here. So these ones will start to peter out and disappear. And maybe you get some interference in the back. They're not so fun anyway. Right? Okay. But it's important to keep in mind that we had a couple of assumptions here. Let's go back to our idea. We limited to small slopes and amplitudes. Okay, so we said the ratio of A over lambda was less than 1, a lot less than 1, right? Right? What does that mean? Where's my good shot? I'm gonna steal this bit of rock chip. Okay, so here's the amplitude of the wave. A. Where's lambda? Okay, here's lambda. So A over lambda needs to be much more greater than 1. So is this correct? That's right. Less than 1. Is this a good approximation?
or yeah, or a.
No,
No.
no, it's garbage, but it's way too steep. Right? But I did it for your eyeballs. Right? So you can understand it good.
A can be small or lambda can be really big.
Right. Correct. Question? Okay, let's do top one. We're doing okay. How do we do path lines again? I know you all studied up on this after I told you to. So I put you up there. I'll start over again. It won't make sense conceptually, but it'll look nice. Okay. So we said something like this, right? Have you done that before? And there's you. Okay. So we're gonna do a fun thing here, and we're going to break apart the motion in a process called linearization. You'll like it. Okay, it's just a mathematical tool. So we're essentially going to say xp is equal to x naught, some reference position, plus that thing. Fun to write that, huh? Okay, and this will be some small perturbation. Has anyone done perturbation theory before? So you have essentially what would be the average of something, of a dynamical system, and you just add a little smudge, right? So this is the average position, and this is the smudge. And what this allows us to do, very similar to a Taylor expansion, is it allows us to ignore terms of order, like multiples of the schmooch, right? So if this thing is this thing to the fourth, it's probably useless, right? Whereas these are going to end up canceling out, as we'll see. Okay. So we essentially will get something that looks like this. You're going to integrate this, you're going to linearize it, you're going to use that thing over there, you're going to integrate it with respect to t. But we don't like integrals in this class, right? Let the computer do those. Okay. So you get your schmudge, okay, of t is approximately minus a wash and yep. Turn room like a day. Yeah, it's Xi. It's Xi, but you can call it whatever you want. A lot Xi.
Like this.
See, this is I knew what was gonna happen. Okay, it's Xi.
Yeah.
It's XSI. I think. Xi. You can practice that? Yeah. In this particular circumstance, we're talking about the linearization of these equations. So what I mean by that is, in order to do a lot of the mathematics that you want to do well in this type of fluid dynamics, you will have small perturbations to what is normal. Larger perturbations will be multiples of this. So when this multiplies itself, we consider it nonlinear, right? Second order effects are nonlinear effects. So we can take something like the actual position of the fluid at any point in the fluid here, and we say, well, there's a mean position and a perturbation from that position. And as long as that perturbation is small, then you can linearize the equations and only focus on what the perturbation would be. Does that make sense? This is a standard technique that we use in dynamics, but it's annoying as hell. Okay. Okay. All right. One of you give me a thumbs up. That's fine. I'll accept it. Okay. And you would do the same thing here with another symbol. So you have Z naught or ZP is Z naught plus, what do they use? Like zeta. Oh, now this one's fucked up too. Yeah. That's not, I didn't do a good job. Not the point. But it has the same functional form, except for some small differences. Okay, it's going to be now A. It's going to have the same bottom, but instead of kosher, it's going to be cinch. Now I'm going to do. You know what these dots mean?
Oh, yeah, same thing.
It means I'm lazy and I don't want to write it twice. It means ditto. Same as the top. Okay. And then here I have the important part. Okay. Okay. So what do you mean approximations? It's not quite a Taylor series yet. So we start with this thing, right? We start with this thing is our u velocity, and we have another one, z, right? That would be the w. And in order to do the path line, we just say, what's the position of the object? Well, it's equal to some velocity, and we're going to integrate it, right? So you would come in here and you'd say, I want to solve this thing since I already know this thing, right? And that's okay, because I can just move this over and I can integrate both sides. Right? But before I do that, I make this substitution. So I'm only solving for a small change. Okay. Then I do the integral. And you believe me. And this is the result of that integral. Right? Kind of looks the same. So that u would be this x. Cos became a sine. Kind of credible, right? All this stuff doesn't depend on t. You might even be able to do that integral. What's the integral of sine? I just didn't want to do it. Okay, so now I have x and z. Another way of saying that, I have cosine and whatever that is. Okay.
The bottom one, the cosine depends on x though? X naught? Or should it be u naught?
What did I write? No, it depends on x naught.
Okay, even though it's pretty big.
Mhm.
Okay.
Yeah, because what we're talking about here is where is it physically located along the wave path, right? The cosine here is modulating left-right motion, not up-down motion. The up-down motion is here in the coches, right? Okay. So you get this. You may not see that you get this, but this is the equation of an ellipse. Why?
Stand block.
Yeah. What's that?
But then you want to know what the
They don't go like
mathematical
this.
units-
Like,
What's the equation for a circle?
whatever your R is, or
Okay, let's do one here. Okay, let's say x is cosine and y is. That's still true?
Yeah.
Why?
That's a trigonometric.
Because it has to be. Because math. So when omega t is equal to 0, what is the value of y? Sine 0 is. Okay, and what's cosine 0? Okay, interesting. There's a relationship here between that picture that I drew yesterday. You all memorized. You said you knew it, right? Not yesterday. Monday. The unit circle moving around here, and x and y. Okay, and if I wanted to squish it in one direction, what would I do here? Good. And that would be an. Yep. So because we look at the solution here, and we see, okay, this piece here, you don't know it already, but it's an amplitude. Okay, this piece here is the one that's varying with time, because x naught, remember we said is the average location. So that's fine. This is where I started, x naught. And let's look in here, z naught. Okay, that's also the place I started. H is the parameter of the fluid. K is the wavelength, kind of. Okay, so this is not changing. A is some amplitude. Okay, okay. So all of this is a number. So number times sine is this piece here, right? Let's look at the other one. I didn't write it good, but it's fine, right? You see how this is? You see how this is still a number? What, cosine? So this never gets bigger than 1. This one never gets bigger than 1, right? Add them together, you have an elliptical motion. Wow. You could have done it. Would have taken you a little bit longer than the book explains it, but you would be able to do this. What do you do here? You start with the stream function, phi. You get the velocities, u. You then look at the path lines. To get the path lines, you simply write this derivative and integrate it. People love integrating, specifically computers or Wolfram Alpha. Once you have that, you can look at the result, right? You could plot each one of these in a stream function, but it was not as informative as just looking at the result and saying, oh shit, I recognize sine and cosine together. That looks like that, right? And in fact, you get this nice little bumpy dough. Okay, questions? Okay, so you have a couple different types of waves as we talked about before. They're going to depend on, where's my, okay. They're going to depend on the depth. So how big is H compared to these other pieces in here? And that's going to tell you how big the oscillation is. Okay, how circular these two pieces are. So this piece here is your amplitude that's found. Now you shouldn't have used A twice, but it's going to be in the numerator. And it's going to change how oblate or how elliptical those ones are. And it's all found in here. And it's the relationship between K and H. Okay. So you have three different versions. You have deep waves. And not surprisingly, if you have an ocean and you have some perturbation on the top of the ocean, that does not then go down 50 kilometers to the surface, right? That'd be weird. Everyone agree that's weird? Okay. Everyone wake up. All right. Intermediate ones. Okay. These ones might push you back and forth. And really shallow ones, the whole thing seems to move. What's an example of shallow waves that you've seen personally? What? Not quite the tide. I want to be under the water now.
A wave pool?
Yeah, like in a wave pool. You ever seen like a video inside of a wave pool and the kelp just does this uniformly? It doesn't look like the top of the kelp is doing this, right? The whole thing seems to be swinging back and forth because you're in shallow water. All the fishes in a line do this, right? Whereas over here, right, you might get jellyfish going in big circles and then the ones lower are doing little circles. Sorry, I should have said sea jelly. Okay. That process makes sense intellectually? Yes? No? Maybe so? Okay. Okay. So let's find the stream function. How would you do that? So you have these U's and they come from this thing, right? We want our streamlines. So let's recall that this thing here, which is going to give us our streamlines, comes from this. Oh God. Yes or no? Where have we seen this before? Chapter 4, maybe? Yeah. It doesn't actually give the one in here, but that's fine. Okay. So this has we're just gonna solve for it. You can do it at home if you want. I know a lot of you want to. So let's look at this for a few seconds and see if we can understand anything about it. If you were to draw that picture, not looking at your book and not just like seeing the answer already, how would you draw the streamlines? Like that? Like circles? Yeah. So this is all the same problem, right? We're just doing a perturbation of the fluid. We're thinking about how to use all these tools that I made you learn.
Do you want the streamline of that?
I got that up there, right? Those define the streamlines. Because that's the stream function. What does it look like? What?
Isn't it just tangent to that? Or am I thinking of something else?
Okay, so we already know that the path line of a particle here is gonna make little circle dudes.
Okay.
What does streamlining mean again?
Is it vector field of where the water is instantaneously going and going at each side?
Right, so it's instantaneously tangent to the velocity. This is the path. That's the result. They're not the same. Yeah, we're gonna have to draw a curve, that's the streamlines. So we have something, I wrote it up there. Can we use that in our intuition to figure out how it should go good? Let's draw the zero contours first. Where's the velocity zero? Middle. Why middle? Okay, let's look at the picture here. Path lane does that, right? Okay, what's gonna happen on this side? Yeah, so let's say this is going backwards. These are going backwards, and then they rotate this way. Notice that nice gyration? Okay, do I have this circle here? This circle exists? What?
More shallow.
Oh, you mean-
Okay, let's imagine they're good circles. You might get me in trouble.
No, like.
Let's imagine they're deep. We're gonna imagine they're deep.
Oh.
Pretend they're deep. Okay. Alright, and in this particular circumstance, do I also have circles on this part? And which way do they rotate? Why do they rotate the opposite way?
You would think because it's like now it's like going down. On that side of the circle, if the path lines are going down, then the velocity must be going down. So then,
On this side of the circle saying.
so no, on the first circle,
Mhm.
on the right side of them, everything's going down.
Yeah.
So the velocities must be going down.
So the velocity is going down.
And then it must be the same on the other side, or else we'd have two different velocities.
Yeah, because if you have it like that, you have a problem.
So they have to going together.
Now, it's just like we saw when we saw convection, right? They have hot, it goes up, like this. And then it moves over, and then it sinks. And if you notice, I can start another cell right here. With the opposite direction. That's all next to each other. You don't have places where fluid is running into each other and stopping. We haven't talked about shocks yet. Okay. Okay.
So then it would be going the opposite.
Is A's negative at that point? Is it easy as that?
What's that?
Is it easy as just that A's negative at that point?
Okay.
That's the opposite amplitude. Okay. Now, there's a zero line. You just notice there's a zero line. And where else is it zero? Here. 0, 0, 0, 0. And the important one,
Okay.
on the
Okay.
ground. No flow going through the ground. Here is 0. Here is 0. Here is 0. Here is 0. Cool. Now what? Uh-huh. A what?
Like a mirror, what's already happened.
Do you want circles?
So it would just look like a large circle under the center point of the crescent trough and smaller circles radiating out to 0.
Small circle under the crescent drop and smaller circles rating up to 0. So remember, if we have streamlines, right? You want to have like each of these be a streamline. We also said the fluid is irrotational, right?
Oh, would it be like following the pattern of the surface?
Kind of. You're gonna have stuff like this. What? Now you can look in your book if you want. What? What is happening? Why does this make any sense? Fucking liar.
The streamline is tangent to the pathline, right?
Change the velocity, right?
It's tangent to the velocity. The path line is instantaneous, is showing the location of a fluid parcel throughout the entire time period. This is everywhere. This is everywhere tangent to the velocity. And recall that that wave is moving. So if you are, I need a thing. Okay. If you're here, the reason why you're going in a circle in the first place is this thing is moving to the right. So let's say you start here. Okay. And now this thing is moving to the right. Okay. Wait, hold on. You're already going down. Okay. And now you go down less. All right. Velocity is slowing down. And you go back up. Brings you around. That make sense?
So the particle just follows like a straight line through the through like the bottom of that second trough, basically, and then you're just gonna see the circle.
Like this? Is that what you're
Just
saying?
like that, and then like the
Yeah, it's a little bit like that, right? Because you do have some horizontal extent here. But remember, when we use the streamlines, the path lines, and the streak lines, we had to use all this information together to understand what the fuck we were seeing, right? Is that more confusing or less confusing? More confusing? Okay.
There's like a particle in that wave, and the wave is moving to the right, so it's experiencing all those different
Yeah.
streamlines as the wave moves.
Right. So the fluid element itself is only going around in a circle as a result of the wave changing the velocities all around it. However, those there are all tangent to the velocity and carry the same velocity along them, right?
So that's how one particle of water moves through the water?
No. No, remember that would be its path line. The streamlines show everywhere tangent to the velocity in the fluid itself.
So it's like where the velocity.
Sorry, so hold on, say that again. Where the velocity is, yes, where the velocity is aiming everywhere. Right. But not necessarily where the particles will go. Because they will now experience multiple objects as they go. It's instantaneous. Okay.
Can you make it use like the speed particle? Like, what would be faster? Would it be like smaller rotations, or would it be the bigger rotations? The particles?
Oh, interesting question. Okay, so what goes faster? What, do these go around faster or do these go around faster? Is that what your question is?
Yeah, like I want to say intuitively, like if there's a smaller distance, you should move faster.
Yeah, you'd think so, right? But no.
Shit.
Why? Yeah. Okay. Yeah, so you could think of it that way, or you could think of it being like the larger amplitude ones have more energy, so they get around faster. But there's a more intuitive way to see it from the equations we've already written. Note that over here in the thing that's doing the turnaround part, right? It only relies on omega. So all of these circles are going to go around at exactly the same rate. Because the only thing that matters is the omega, right? Now K, of course, as it gets larger, the wavelength, that's going to affect omega as it did over here. But we're imagining one wave, okay? Okay, we did not get as far as I wanted to today, but that's okay. We're gonna be fine. All right. We have some approximations that are pretty cool. And you'll learn how tsunamis work. I'm just gonna really briefly talk about some words, and you can immediately forget them until you read them again in your next class. One of which is, we haven't looked at the energy yet, but in any system, usually in classical systems, you'll talk about, the potential energy and the kinetic energy. And an important thing to keep in mind is the equipartition of energy. So some of it will go into kinetic energy, and some of it's going to be stored as potential energy. And you'll just pay them back and forth, right? You've seen that before? Okay. I'm not gonna write anything on the board. But let's talk about approximations, specifically deep and shallow. We talk about dispersion. So we talked about deep, intermediate, and shallow waves here. Let's look at, I maybe should not have thought. Oh well. That thing that I just erased, I read, but I'm gonna write it. I'm gonna write it. Wait, this is not. Yep. What do we got? It's gone forever. So this is for our deep water. Okay. So for deep water, let's make that into a statement. H over lambda is greater than 1. H. Here. That is larger. Okay. So go ahead and show me what tangent of x equals when x goes to calculator.
Oh, okay.
Yeah, calculator, right? The tangent of x as x goes to 10,000.
Hey,
Yeah, tangent. Yeah, the tangent of x. One. Oh, interesting. So earlier, I really wish I hadn't erased it. So stupid. Okay, so we had this other shit in there, right? And as x goes to 1, or x gets really large, as this value, h over lambda, gets really large, you can write your dispersion relation really easily. You can say C equals 3 over K, with all the other stuff, with the tangent stuff, right? You can say X. Let's say that becomes 1. Okay. in the deep water relationship. Another way of saying that is the square root of G lambda. So this type of wave is dispersive or non-dispersive? Or what did I just mean by that?
Versus you got just like it feeds in the data and so it's farther from the border. Is that what you mean by dispersive?
Not exactly.
Okay. Dispersive doesn't separate based on wavelength?
Exactly.
Oh, okay.
So does this separate based on?
Yes. Because it's dispersive.
Exactly, right? So this means it's dispersive. Okay. Right? And so the dispersion relation depends on lambda. Dispersion relation, does it disperse? Yes. So for deep water waves, they disperse. They separate. Okay? Interestingly enough, what happens for shallow waves? Over lambda, which less than that. Close to zero, what does Hansch do? What? Zero? No, that won't be helpful. The wave would be zero. We'd be done, we get to leave.
So is tangential close to zero?
What? Yeah, so now we're gonna ask the question. Okay? As Hansch of x, as x heads towards zero. We all know how to do this because we're like calculus. What did you put in there? You put 0.01 and you got 0.01 back?
No, I don't. Point oh. If I-
Put more zeros. 0.01 is not quite close to zero. It also goes to zero. It doesn't go to zero.
That's what I do.
It goes to X.
Oh.
Yeah, it does.
Is that kind of like?
Got it.
Oh,
That's exactly what the small angle.
okay. There we go. We should.
So it's small angle approximation. So all of them we use every day, right?
Yeah, I didn't know that we can use that for. Yeah.
Okay. And so that instead will take this C. And I'll give you something sort of strange, but you'll love it. G H. Not dispersive. Yeah, so when you look at the shallow wave approximation there, which is steep, you'll now have non-dispersive waves. Okay?
Like the way you stay like that.
So if you have some wave group that's coming in, let's say you form waves out here, create a plunger or something, drop a rock, and they all head out in different locations. But let's say a wave packet is created near the shore, for example, okay, then they'll stay together.
Oh, oh.
So that's why we get like tsunamis from jet flows earthquakes.
There you go. That's exactly what we're talking about. So what you see there is that H over lambda, much, much less than 1, when the tsunami has a large lambda, right? Even if the H's are big, you have non-dispersive waves, right? So let's think about that for a second. How big do they have to be? How thick is the ocean? No one knows?
No.
Is it order of magnitude? We're physicists. We don't care.
Wait, so how big is the ocean?
Yeah, how big is the ocean?
Oh, I thought, okay,
Yeah, how deep is the ocean?
oh, how deep? Oh.
What? Did you see 30,000 feet in a physics classroom?
That's a net.
I don't know, like a half a gallon.
Maybe a couple corners.
Two boulders the size of a small boulder? No. It's deeper than a pool. Good. What? Couple kilometers. Okay, so first let's start with the word kilometer. Good. Couple, that's fine. You want to go deeper? Let's do 10. We like orders of magnitude. So 1 is couple, 10 is the second order of magnitude, 100 probably too deep. Okay. So let's think about that for a second. If H is 10 kilometers over there, how big does lambda have to be?
A couple order of magnitude larger.
Yeah. So like 1,000 kilometers,
Oh.
right? If that's the case, then you get a solitary wave moving. Right?
Really?
Yeah. Okay. And you can,
Because it's not dispersed, if all the waves superpose on top of each other.
and all the energy doesn't dissipate.
Oh.
Yeah, we haven't talked about the energy at all, but that's the reason why everyone sucks when a tsunami hits. Makes sense?
Is that what a soliton is?
That's a rogue wave, yeah, yeah. And there's a solution for rogue waves in here that I thought about giving to you as a problem. I think it's on page.
The solution of rogue wave as if like we're solving it or like.
Yeah, so if you go to page 384, it talks about in figure 824. I didn't include it, did I? Oh, okay, well, I fucked it up. It talks about solitary surface waves. There's a couple of solutions to the wave equations that are just like fun shapes, including what are called sinusoidal waves. We're just not going to do them. We don't have time. We barely have time to do what I want to do right now. But what I want to do is waves on a density interface. We're gonna have time to do this. Okay. No, we don't have time to do this, but we're gonna do it anyway. Questions about these before we move on to stably stratified fluids? Okay. That's the worst eraser. Okay, we're gonna do this really quickly, and you're still gonna understand it, and you're gonna love it. Okay. This picture, we're gonna skip over the dispersion ones, but learn them. This is how crests disperse, like crest rays. So this is like how streamlines or wave crests will work around something like an island. Waves come in, and then this is more shallow. They bunch up here. They're also going to bend around the island. This is not how light works. Yeah. Yeah, they look similar, but it's not exactly. And they're very different mathematics, obviously. Light is dispersive for totally different reasons. Yeah. Okay, cool. Oh my God, got him. Wait. All right. Okay. So we didn't talk about this, but when we were doing Bernoulli equation, you make some approximations to the Navier-Stokes, you make some approximation to mass continuity, and you kind of just roll with it, right? You say this type of fluid can do X, Y, and Z, and it can't do other things. So I want to think for a moment about the air that we live in. Okay, we live in a fluid at the bottom of a fluid ocean. Okay, so right now there is basically a flat layer of air whose properties are very similar. And if I go up slightly, the properties change, right? And if I go up above that, the properties change more. And as I go up at every layer, you can think of it as being stratified. There's stratification, right? So we can say there's preferred direction, and horizontally there's not. And we can write these, okay? So we can say something along the lines of d rho dt equals 0, and du dx plus dv dy plus d omega, sorry, dw dz, it's not an omega, it's 0. Okay. And we can talk about the rate of change of the u component as only being due to horizontal gradients. And I could write the same thing, I guess, with the rest of them. But we're gonna write them slightly different. Let me just write this one with its friend dv dt. And this one's gonna be separate. That's right. The fuck did I do and why? Okay. In a single layer, okay, the motion in x and y, so that's this direction, right? Remember z is this direction. The density is basically the same. Okay. Density is only changing in this circumstance, maybe with temperature or height. I'm choosing this stably stratified medium. And the pressures then in x direction cause the fluid to move. Okay, so there's a high pressure over here and a low pressure over here, causes motion. There's no change in the gravitational potential energy, so there's no reason to include a term here for gravitational. Okay, same thing is true here. That's just why. So those are the same. But this is different. So these are our vertical motions, and they only come from the balance between pressure forces, which are dp dz, and our gravitational potential energy. Okay, but they're with respect to a reference pressure. So I know that's going to look annoying to you, but you're going to live. I promise.
This is about as pressure, P naught,
What's that?
so that bottom is P naught,
No, these are rows,
so they're right.
but this is a reference. Sorry, I should have said density. There's a reference density, not a reference pressure. I apologize. Okay. Okay. So I told you before, we do linearization. We're going to do linearization again. And in fact, you can linearize these equations. And you can write something as simple as P is equal to a reference P bar. You want to know what the bar means? Average. So it's the average value plus a perturbation. Look, we saw it 2 times in one day. Maze. Right? It's almost like I planned it. I didn't. Just kidding. Okay, and then the same thing's true here. You have rho, which is rho z bar plus rho. Okay. So you can do that here. You can collect all your terms together. You can put these in, and you'll get something really interesting. You get something like you say, okay, that doesn't really look like it helped us at all. Why would you do that, Mateo? Okay. We're going to introduce something called the Brunt-Väisälä frequency. This is just a definition. And the reason we want to do this is because we see that this piece here is this piece here. Okay. So if I know what this is, which is the average density gradient as a function of z, which is something that might be described in the fluid itself, okay, then I can just pop that right in here, right? And I can write this as Okay, you hate it, you hate it, you hate it, right? No? Yes? No? What does it mean? Intellectually.
Kind of thing that there's some sort of contradiction going on, since it's like.
Okay, there's one more step we can do here. We're running out of time, and I just want to show you the pretty picture because it's really cool. When you see something with a time derivative and an n squared, that's already your hint. Brunt-Väisälä frequency is telling you about the frequency in which an oscillation is going to occur. We can go through this more on Monday at the very, very beginning, but I won't spend too much time on it. Other than to say, the very first week, I think, we talked about what happens to a parcel of fluid as it moves up in the atmosphere. If it gets to a certain place and it's colder than the surrounding air, it sinks again, right? And then it goes back down, and now it's hotter than the surrounding air, and it goes back up. That is this, right? Some parcel moving up and down in a suspended, stably stratified medium. That frequency, the Brunt-Väisälä frequency, is telling you how quickly those oscillations are going to happen. And because the solutions are generalizable, this thing can become imaginary or negative and negative inside of a double, inside of your cosine I solutions. I'm not gonna be able to show you here because we don't have time. But essentially, that would be your convection. So rather than them returning back to where they came from, they would get larger with amplitude. Right? There's a deep connection between exponentials, which have an imaginary component, and the sinusoids. Right? And it explains all of the different types of clouds that you see here. Okay, so this is just like something to walk home with at the end of the day. You have a temperature gradient that's going up like this. And all of what you see here is due to variations, what we call gravity waves, inside of a stably stratified medium. There is no convection in here. You say to yourself, that looks like a circle, Mateo. Why is this circling? Because it's like that. Not exactly like that, but it's in the lee part of the mountain. And so you get these rotor clouds in the back of it. And they create waves all the way up. You get these really beautiful patches. Street clouds. You ever seen like a street cloud? The long cloud like this out of the board?
Yeah.
Then there's an empty space, and then there's another long cloud. Okay. Okay, sorry. I want to go into more detail, but I guess.
Are we at for lenticulus? Here.
Yep. Yeah. Questions, comments, concerns? Yeah, as usual, I can't get through the material fast enough. I'm sorry. Yeah.